Hi guys, I've previously shown a video where we have made this battery-powered temperature sensor for indoor usage, and in this video I'm going to modify that one to have it DC powered, and it's going to be the same model for the top here, so the lid, the major part of it is still the same. It's like a screw that you screw on top of your sensor. Very nice to work with, I think. And instead we have printed this model that you can see in the field below, and it's a bit thicker, as you can see, and that's just to be able to get the cord in and out of here. There's also a mounting here, which just push down in here, so you have the cord coming up here, and then you can have screw connectors, a small board here that I will show how you can do this connection. I have one earlier prototype here, and I will show you the steps that I've taken here. And here is just a screw connector for and also a step up, step down circuit. But I will instead for this construction I will still use instead I will use a really good voltage regulator to get a good stable 3.3 volt. And key here is I still remove the voltage regulator that is on board of the Arduino Mini Pro, and also the power LED. And the reason for this is to get rid of all the circuitry that can dissipate any power. I mean, you have milliamps going here the whole time if you have bad voltage regulators that you always have on this at least the counterfeit Arduino Mini Pros. And that can or will actually impact, if you have this in this compartment, it will actually make the temperature rise slightly on for the sensor down here. I will also replace, this is the non-high power version of the RFM69 chip, and I will put in the high power one here also now, since I have the extra power when transmitting. But it's no problem that there's any power or heat dissipation from here, because it's a really short time that it's switched on when transmitting. For this project we will need, of course, an Arduino Mini Pro, and as you can see there's a quite large amount of these Arduino Mini Pros that are I consume quite a lot of these for any kind of sensor projects. I use these cheap ones from China, so you can order them 10 or 20 at a time. I've never had them fail on me, actually. And the only thing that is bad that we're gonna fix now is to eliminate the voltage regulator and the power LED. That needs to go away. So let's start with that. Now we have removed the power LED and the voltage regulator, and I really recommend that you program the chip to really make sure that you didn't accidentally tamper with anything, and just burn something, maybe in a sample sketch or something, to make sure that it looks okay still, before attaching more components to it. But let's get started on doing that. First we're gonna attach the radio and then the temperature sensor. So now we have soldered everything for the actual sensor, and now we're just gonna add a better power supply for this one. And I'm gonna use this standard type of prototyping board, but I'm gonna make it a bit prettier. I don't like very much the color of these ones, but they work fairly okay. So I'm just gonna put some spray paint on it, and I've made a small 3mm hole here. So we should we'll add an insert here of an M3 and just melt it into here, and yeah, so it's these standard inserts that you can have for M3 screws. And then we're going to mount this one here. We're going to have a screw connector for attaching the incoming USB cable, and then there's going to be two ceramic capacitors here of 1 microfarad each, one on the input and one on the output. And then it's the microchip voltage regulator that has a really low dropout and low cosine. So it's excellent to have this for to don't get any power dissipation. But let's do that then. The sensor is now ready, and I'm going to show the difference here between here. I was using my own little board with a better voltage regulator on it, and compare it to this step-up circuits. I mean, both of these two will do the trick. What we're after here is to really get as low power dissipation here inside the sensor, even if we have it powered. So basically we'll operate like it would be in deep sleep and the battery mode. Yeah, and this is a step up down circuit, so it can accept voltages in the range of 1 volt up to 6 volt or something like that. So it's that's good for many applications, but we can look at the characteristics on by looking at the power consumption here. So we start off with we can start with the one that I already had from before, and to be able to measure the current here, or how much energy we pull from the DC outlet, let's hook that up to our current ranger, and we take we get the input here from the screw connector, so it comes from the DC power outlet, which is a standard USB charger. This one is on 1 amp, but you can have smaller also, of course. And then you take the other end, out from the current ranger, and connect it to the step up down buck converter here, like that. And if we look at the power consumption, you will see quite high values initially. This is, since it's transmitting, you can see the LED is blinking here also, that we are transmitting here, sending information about the sensor, etc. This is only done at boot up. And now you can see that we are down on 0.0 milliamps. So we switch it to microamps, so we increase the sensitivity. And then you can see that it goes from everything between 0 up to 200-300 microamps. Quite hard to get readings on this, and that is due to the nature of these step up down buck converters. And if we want to look more in detail on this, so it's really hard to say what is the actual power consumption here. So if we hook this up to an oscilloscope, we can see this more in detail. And this is also quite simple if you have something like the current ranger. Let's start it up. So we can hook this up to in the same way that you can hook up a multimeter. You can attach an oscilloscope like that. And then we can see the actual shape of what is happening here. So what we're actually measuring here now is current. Even if it says millivolts, this translates then into the equivalent one of microamps. We can take one. We can see actually the mean value for this is 200 microamps. So even if it goes everything between 0 up to 300-400, it's really hard to draw that conclusion. But in general, we are at around 200 microamps with this step up down buck converter, which is fairly good. I mean, if we just had this kind of load in sleep mode, I mean, we have it still hooked up to Arduino, it's sleeping most of the time, it will still last for maybe 2 years on 2 pairs of AA batteries with that kind of power consumption. So fairly okay. I mean, we don't have lots of power getting lost here and transformed into heat. If we look into our newly built sensor, so the only difference here, it's the same kind of circuitry on this side. It's only to replace this step up buck converter. We can do that later. So we have it here then, and you can see the small board here. So we'll remove the screw for like that, and we hook up the current ranger. So this is then going into the board, so this is out from the current ranger, and we then take from the DC power outlet, and that is the input. And as you can see, initially we have the same phenomenon that we are transmitting data, so it's up at 20 milliamps or even 40 when transmitting. It's when it's receiving that we're using 20 milliamps, but this will then soon go down to 0, and you can see then what kind of power consumption we get from this board. And we will then switch over to the microamps, so we can actually see it with a more fine grain, and then it looks to be around 70 microamps that we are using. And you can see that over here on the oscilloscope that it's probably more in the range of 120 microamps if you look at the mean and both the cyclic RMS. So it's really hard to capture this kind of transient stuff. As you can see here, I can do the auto setting here so we see what's going on. You have this noise going on periodically, and otherwise it's a much more steady voltage consumption here, or power consumption here for the voltage regulator. So again, if we compare it to what we had with the step up down circuit, that was maybe 200 microamps, and then it's more in the range of 120 for building your own voltage regulator board. Here we're using the microchip LDOs, and yeah, so it's that was the main purpose of showing here, that you can get a bit more steady, but both solutions are perfectly fine for it. We will have minimum power leaking out here into the casing. So now we have built our DC powered temperature sensor. Thanks.